a study of different replacement policies in IP stride, GHB and FDP prefetchers. Prefetching is a technique to fetch data from the DRAM into the cache before it is needed by the processor. This is done in order to improve the IPC and hence the processor's performance. It is necessary to carry out efficient prefetching because this would prevent cache pollution by only loading data that is required. Here we talk about three prefetching techniques, namely the IP stride prefetching, global history buffer with constant stride prefetching, and feedback directed prefetching. Out of the two, IP stride and GHB are unicore prefetchers, while FDP is a multicore prefetcher. Multicore processors face an issue when one of their cores carries out aggressive prefetching, due to which the rest of the cores can't prefetch. And FDP solves this by adjusting the prefetcher degree based on the accuracy and lateness. FDP specifically comes into picture when multi-core systems have to be developed with multiple prefetchers. It is necessary to have effective and good replacement policies, as we generally have a limitation on the size of index tables that we use to store the IP addresses. So here we've discussed about three different replacement policies. They are the least recently used LRU, least frequently used LFU, and a hybrid of both policies. It is generally good to have an IP index table replacement policy along with an effective prefetching technique which will boost the performance of the processor. Prefetching is a method used for hiding latency and is an attempt to overcome the evident memory wall. We have reviewed a few prefetchers from the Data Prefetching Championship, the first one being AMPM. This technique uses a bitmap-like data structure that is mapped to the memory region. By analyzing the access pattern of the memory, it can prefetch data independent of memory access order and instruction order. This makes it highly efficient and useful for applications with irregular access patterns. Next, we have the box offset prefetcher, which is a more aggressive prefetching technique that automatically rotates the offset value to produce timely prefetches, making it an efficient technique for making memory-intensive applications more fast. Lastly, IPCP divides the instruction pointer into classes based on how they were accessed. Small and specialized prefetchers are then fed with IP categories, making it an effective technique for spatial hardware prefetching. Here listed are a few other prefetching techniques that we have reviewed. FDP, PADC and HPAG are a few multicore prefetching techniques. Of the three, FDP is a more fundamental prefetching technique based on which the other two were developed. And in the recent time, prefetchers developed include the domino temporal data prefetcher, bingo spatial data prefetcher, and the multi-look-ahead offset prefetcher.
The first prefetcher we implement is the IP stride prefetcher. This is generally used in codes where we have a lot of loops that are traversing through arrays. As seen in this particular code snippet, we have a nested loop and array B is being accessed in a nested loop fashion. Consequently, the fetch sequence of B will be in the manner of B1, 1, B1, 2, B1, 3. As we can see from this, there is a constant stride between the data of B that we're accessing, and this stride changes only when we're accessing a different row of B, as in it's moving from 1 to 2. But from the observation that there is a constant stride between most of the data between the array B, we can go and prefetch this data of B and keep it ready so that it can be used later on in the program. The IP stride prefetcher works by storing a table of IP addresses along with its last miss addresses, the last stride and the LRU value. The LRU column is solely used as a replacement policy for this IP table. For example, when a new IP comes into this table, it first needs to be entered into the table, and the entry that will be updated with this new IP will be the one with the highest LRU value as seen here. Consequently, when we update this, since this becomes the most recently used, this changes to 0. And all the other LRU values are updated and incremented by 1. Similarly, if there's another IP coming in, that will be entered into the table with the highest LRU value, and the LRU value again gets incremented, and the one that is most recently used becomes 0. Similarly here, a new IP X35 is coming in. I'm just showing this to fill up the table to show the actual working of the IP stride prefetcher. Now in this table comes the part where we are trying to, we have an IP with a misaddress, but this IP is already present in this IP table. and it has a history of a last address which was 0x70, and the current misaddress is 0x72. Thereby we can calculate the stride of this as 0x72 minus 0x70 and have a stride of 0x02. And consequently, after this stride calculation, we will go and prefetch data from this latest misaddress, and we will keep prefetching it up till the prefetch degree into the stride value. Similarly, this happens for another IP that is already present in the IP table but with the last misaddress of 0x40. So the calculated stride is 0x46 minus 0x50, and consequently the prefetching happens in the manner shown here. The second prefetcher we implement is the global history buffer constant stride prefetching. This is an implementation on top of the IP stride prefetching we saw before, except that it decouples the tables into two so that we can store a more complete history of misaddresses. This is done by storing an index table and a global history buffer. The index table consists of the IPs along with pointers to the global history buffer. The global history buffer consists of the misaddresses and pointers which point to within the global history buffer entries. This global history buffer is accessed by a head pointer in a circular FIFO fashion. Let's say an IP of 0x23 comes with a misaddress. In this case, the IP is entered into the index table, just like what we saw in IP stride prefetching. However, the misaddress is entered into the GHB, wherever the head pointer is pointing to. Once this is done, a link is created from the IP index table entry to the GHB entry with the corresponding misaddress. After this, the head pointer is incremented to point to the top of the circular GHB FIFO. In the same way, when another IP comes in, the misaddress gets updated in the GHB, head pointer gets incremented, and a link is created from the index table to the GHB. Now let's say another misaddress of an IP that is already present in the index table is coming in. So in this case, what we do is we update the current misaddress into the GHB, increment the head pointer, then we create a link from the index table to this most recent misaddress. Subsequently, we create a link from the most recent misaddress to the previous misaddress. In this way, we can see a linked list structure being formed to store misaddresses of a particular IP. In the same way, for another IP 0x25, there is a linked list structure being formed. Now let's say we have another misaddress of IP 0x23 coming in. We form the linked list structure by updating the GHB pointer. Now we see that there are two stride informations that we can extract for this IP, which is stride, which is 0x54 minus 0x52, which is the stride value, and the previous stride, which is 0x52 minus 0x50. When we see that the stride and last stride are equal, we go ahead and prefetch in the same manner that we saw in the IP stride prefetching. As the prefetches keep going, we may get a case where the entire GHB buffer is filled up with links from the index table to the GHB buffer misaddresses. And the head pointer goes and points to the beginning of the GHB because it's a circular FIFO. Now let's say an IP 0x27 has a misaddress. This misaddress will have to be entered into the first entry of the GHB where the head pointer was pointing to. But now that we add this misaddress corresponds to the IP 0x27, which is the link shown in pink. However, we did have a link in blue for the IP address 0x23, which was there previously. So whenever this happens, we have to make sure that we invalidate this pointer so that we do not go around fetching based on misaddresses of different IPs as the GHB keeps getting filled. Feedback directed prefetching is a method to dynamically adjust the prefetch degree of the prefetcher based on certain dynamic runtime information that we get. This FDP is implemented on top of the GHB structure. The two parameters that we keep track of is the prefetcher accuracy and the prefetcher lateness. There are counters that are used to keep track of the number of useful prefetches, the number of late prefetches, and the total number of prefetches in order to calculate the prefetcher accuracy and prefetcher lateness. However, we sample this feedback information on every 1,000 instructions, and since we are sampling this, we need to make sure that we have the feedback from the previous interval as well as the present interval. Hence, at the end of every interval, we update the counter value based on the counter value at the beginning of that interval and at the end of that interval. A dynamic counter value is kept track of and determined based on the prefetcher accuracy and prefetcher lateness. When we calculate prefetcher accuracy and lateness, we compare it to these thresholds and determine if it is high, medium or low, or late or not late. The dynamic counter value initially is set to a value of 3, which is a middle of the road prefetcher, which is not too aggressive nor too conservative. Based on the accuracy and lateness, we either increment or decrement the counter. As we increment the counter, we make the prefetcher more aggressive, and as we decrement it, we make it more conservative. And based on this value, we adjust the degree of the prefetcher from 4 being very conservative to 48 being very aggressive. In this way, the prefetch degree is adjusted dynamically based on the runtime information of the prefetcher.
LRU is a replacement policy that replaces the least recently used entry from the table. Here, A is the first entry into the table and its LRU counter is set to 0, which is shown within the square braces. And every time a new entry comes into the table, we set its LRU counter to 0 and increment the LRU counter for all the existing values in the table. With C and D being introduced into the table, we have a full table with all of them having their LRU counters values incremented and D set to 0. And now when the table is full and we have a new element coming in, we check for the value with the highest LRU counter, and that is replaced with E and its counter is set to 0. Now when we again find some value which is again within the table, that simply sets the LRU counter to 0 and the remaining is incremented by 1. And again when we find something which isn't in the table, we again go back, check for the highest LRU values and replace the one with the highest LRU and set the counter value to 0 for F. LFU is a replacement policy in which the table entry which has been accessed the least number of times in the past is replaced with the newest entry in the table. Here this is done by having an LFU counter for every entry in the table. This data shows the table being filled at some point in the execution where every data packet has been accessed a set number of times. And here every time a data is accessed which is in the data table will have an increment in the LFU counter and so on. But when there's a new entry which isn't in the data table, we tend to look at the counter values of LFU, and the one with the least LFU value is evicted from the table and is replaced with the new data entries, and the counter value of LFU is set to 1. From the LFU and LRU schemes that we just discussed, we built upon it with a hybrid scheme which uses both of them. Here we have a table that runs two counters, one for the LRU and one for the LFU, and when a new data element is encountered, we check for the data element in the table with the highest LRU value and then go on to compare its LFU with a preset threshold value. If the LFU value is greater than the threshold, we do not evict it and go on to search for the next highest LRU within the table. And again compare the LFU, and this process continues till we find an LFU value that is below the threshold, and that data element is evicted from the table, replacing it with the new data element and its LRU counter set to 0 and LFU set to 1.
To start, we measured the machine cycles of each prefetcher for each benchmark and compared them to a core without a prefetcher as well. We also compared the machine cycles of each prefetcher using all three replacement policies. Next, we evaluated the IPC values for each prefetcher and compared them to each other. We also evaluated the IPC of each prefetcher with all three replacement policies. We then determined the number of prefetch hits for each of the three prefetchers and the number of prefetch hits for each prefetcher using all three replacement policies. Lastly, we measured the number of useful prefetchers for each prefetcher as well as the number of useful prefetches for each prefetcher using all three replacement policies. Now coming to the analysis part, we observed that the hybrid policies machine cycles are least in IP stride in GCC and POP2 benchmarks. We reason that it is due to the policy's ability to work both on spatial and temporal locality. For Fortnic 3D benchmark, the LFU machine cycles are very high across all prefetchers. It is due to the access pattern of this benchmark, which is better suited to other replacement policies. There is also a possibility of this benchmark not having enough temporal locality for LFU to work its magic. We also observe that for GCC and POP2 benchmarks across FDP and GHB2, hybrid scheme performs well due to the temporal and spatial locality in terms of machine cycles. FDP fares the best in all prefetchers in regard to IPC. This is due to its well-suitedness to these benchmarks as well as its variable prefetch degree. We also find that the IPC for hybrid scheme is most in IP stride prefetching. We also find that there is not much change with respect to replacement policies in FDP prefetcher. We theorize that this is due to FDP prefetcher's well-suitedness regardless of the replacement policy. Except CAC2 BSSA, the IP stride prefetcher performs mostly similar to both LRU and hybrid prefetcher with respect to prefetcher hits. We theorize that due to the complexity of memory access pattern of this benchmark, this happens. The hybrid LRU LFU scheme in GHB prefetcher performs better in terms of prefetcher hits compared to other two replacement policies. This may be because of the hybrid LRU LFU scheme can strike a balanced approach between the two replacement policies and utilize the strength of both. Similar to GHB prefetcher, FDP prefetcher's hybrid LRU LFU scheme performs better in terms of prefetcher hits compared to the other two replacement policies. Again, this may be because of the balanced approach of hybrid LRU LFU scheme. Useful prefetches are more or less the same across all three prefetchers. This indicates that the prefetchers are doing a similar job of predicting the memory accesses that are likely to occur in near future. When it comes to useful prefetches, LFU underperforms as compared to LRU and hybrid schemes in all benchmarks. This could be because LFU prioritizes recently accessed blocks over their frequencies, which may not always reflect future access patterns accurately. Consequently, LFU may struggle to predict memory accesses precisely and prefetch the necessary data. Now coming to the conclusion part, in our study we evaluated different replacement policies for three prefetching techniques, IP stride, GHB and FDP across various benchmarks. Our findings suggest that the hybrid LFU LRU policy works well for IP stride in terms of low machine cycles in GCC and POP2 benchmarks. However, the same prefetcher with LFU policy performed poorly in the Photonic 3D benchmark. Similarly, the GHB prefetcher's LFU policy also performed poorly in the same benchmark, while its hybrid LFU LRU policy performed well. We observed that the FDP prefetcher performed consistently well across all benchmarks regardless of the replacement policy. However, for GHB and FDP prefetchers, the hybrid LRU LFU scheme performed better than the other two schemes, indicating that a balanced approach is better suited for these prefetchers. While useful prefetches were similar across all prefetchers, we found that the IP stride prefetcher with the hybrid scheme produced more useful prefetches than the other two replacement policies across all benchmarks. Additionally, the LFU performed poorly in terms of useful prefetches compared to the LRU and hybrid schemes. Therefore, we highly recommend using a hybrid LFU LRU policy for the IP stride prefetcher and for GHB and FDP prefetchers as well. However, it is important to note that different benchmarks may have varying access patterns, and thus it is recommended to perform the detailed analysis for each benchmark to determine the optimal replacement policy for each prefetcher. These are some of the references. Thank you, and any questions?